Hey dudes, we are checking out sort of a double header of 5.4 and 5.5. We're looking at first the derivative of logs, exponents, and trig, and then we're going to look at the product and quotient rule about how you take derivatives of something that's multiplied or divided. It's kind of heavy, but hang on. All I want you to hold tight to is that the slope of the tangent is the value of the derivative at that point. So if you're talking about this point, f prime of 2, all the derivative at 2 is the slope of the tangent line there. Cool. One way we talk about derivatives as f prime of x, or we can also use dy dx, depending on which one you prefer. So let's try this out. We can find the slope at a certain point by hand. We learned yesterday that if we took the derivative of this, we saw the trick that you take this and multiply by the coefficient in front, and then this piece is sort of negated. So the derivative of f prime of x is really 2x. And if you evaluated that at 2, right, f prime of 2, you'd get 4. So that's the long way to do it. You can also use your graphing calculator. You can do that graphically like this. There's sort of a shortcut down there, but you can plug in the equation that you were originally looking at. So get your head out of the way, G. And there's a squared, and there's the 5, and if you graphed it, 6. It would look like that. And you can find the derivative at a certain point by saying second calc, and this number 6 is dy dx. So I'm going to go down there and say OK, and it says what point do you want, and you can say I want point 2. Tell me about 2. X equals 2, and it says, hey, the derivative there is 4, just like we thought. Another sneaky way to do that is this math and n derive. And so you can, in the math button, you go down to n derivative, and it says, hey, let's go dy dx. You plug your x in there, just saying that we're using the x value, and then plug your equation in, so x squared plus 5 was what we were using before, and evaluate at what x value. How about 2? And there's 4. So there's mathematical ways to find the derivatives at all those points. Cool. So you can check my calculations as we go to make sure I'm not making stuff up, but I want to be able to take the derivative of trig functions, and there's interesting derivations of how these work, but I think you can just see them if you think about slope, right? So if we're primarily talking about the sine curve, so that's this blue curve, like that. We're interested in the derivative at all those pieces. If you think about the slope here at point A, this slope is flat, right? It's that where it tops out. So the slope there is 0. So I'm going to put a dot down here at 0. And the slope here, down here, right, is 0 also. And the slope here is 0 also. And the slope here, if you were careful with it and looked at it carefully, it's a 45-degree angle. And so the slope is 1 over 1, rise 1, run 1, right? And so its slope is 1. And here at this point, the slope is going downhill, and the slope is rise negative 1, run 1. The slope is negative 1. So all of these points lie on the cosine curve. And so the derivative of sine is just the cosine of x. It's just looking at the slope at all these different points. It happens that they are on this cosine curve. And so they're corresponding. You can do the same thing with cosine if you looked at cosine, but they're on the negative sign. And tangent is the big uglier, a little bit uglier, but fear not, they're all in your calculus section of your formula booklet. Cool. So we're just going to like throw them at you and then work with them a little bit. You don't necessarily need to know why they are that much, but I think this one at least makes sense, that the sine's derivative is the cosine. Okay, so we can also take the derivative of the natural log function, and if you plotted this curve and you played this game with the calculator, you could find the derivatives at all these points. If you took this curve and you chose like 1. This has a slope of 1. If you picked a half, right, because now we're half in, this has a slope of 2, or maybe you call it 2 over 1. If you picked 4, this has a flatter slope. That's not quite the slope. This is a slope of 1/4 at 4, 1 at 1, 2 at 1/2, and here it goes down to infinity. This is the case then that you have this inverse of the x value. So at 3, your slope there would be 1/3, and at 6, get your head out of the way, G. At 6, your slope would be 1/6. So natural log has a nice, an interesting derivative in that the slope is always whatever this x value is, but 1 over that. All right, so we'll use that again. Also, it's right here in your notes. Here. Okay, and here's another one that you can use. That's if your function is e to the x, the derivative is e to the x as well. And you could plug this into your calculator to see that that's so, but it just means that the slope at any point is still e to the x, which is an interesting quirk. We're going to use those. You don't necessarily need to memorize them because they're here. What I'd like to use those with is the product rule and the quotient rule, and that part I wanted to show you like this. If you were trying to find the derivative of this, one way you could do it is maybe multiply them together first, so get 6 to the 11th, and then take the derivative like we used in 5.3, which would be to multiply this exponent to the coefficient, so 66, and then decrease the exponent by 1. So that's what it should be, right? And you can ask Wolfram Alpha, and Wolfram Alpha says the same thing. If you weren't able to take the derivative of each piece, right? If this was f of x and we were trying to take this, I want to know is 66 x to the 10th what we get when we take the derivative of this and multiply by the derivative of that. Well, so the derivative of this would be 4x to the first times, this would be what, 27 x to the 8th. That's 108 x to the 9th. And so that's not what we're supposed to get. So this trick doesn't work. You can't just take the derivative of one and multiply the derivative of the other and get the equivalent of the derivative of the product. There's another thing that works. It's what we're going to check out now. Okay, so I want to show you the derivation of the product rule. It's the derivation when you have two functions that are being multiplied, hence the product. Fast forward.
So if you work this back to first principles, you can think about this as the limit as the offset goes to 0. And you can talk about the two offset y values minus the two standard y values all over the offset. Just going back to first principles in that way. If you take that then and insert this, right, this is this piece and this is this piece. If we insert this component, it's basically 0. It's minus all of this plus all of the same. So really we haven't changed anything. But what we can do then is break this piece apart. Get out of here, old guy. You guys are probably saying the same thing. If we take this piece and break it apart and use it with this, all of this is here. And I'll show you why. We'll do that in a second. And all of this is here. Okay, so far so good, sort of. What we can do with that is factor out this vx plus h and vx plus h, and also factor out the ux and ux out of here. And that's where this comes from. So here's this vx plus h that we factored out here. Here's this ux that we factored out there. And now it's looking a little cleaner. This limit, as h approaches 0, it doesn't change this because h isn't involved in there. So what we can do is pull that piece out. We can also pull out this piece, so that's where this comes out of the limit. So that's here. And then likewise, this piece we can actually take the limit. So as h approaches 0, this is just v to the v of x, and that's what this is. So we pull out the vx, pull out the ux. And now we have this whole thing. And if you think about this piece, that's really just the derivative of u, right? This whole thing is the derivative of the u. And this whole thing is the derivative of x, right? It's just like going back to the first principles piece.
So we have the product of these two things is the multiplication of the second by the derivative of the first, and added to that the first function times the derivative of the second. Cool, here's a nicer way to look at it. If you're trying to get u and v and multiply them together, right, and you're trying to take the derivative of it, derivative of the first times the second plus the first times the derivative of the second. Another way to look at it. Cool, here's a different notation if you like. Okay, that's also in your notes, but we'll use that enough that I think that you'll just remember it. So derivative of one times the original plus the original of the other times the derivative. Great, so let's try that out. Looks scarier than it is. So let's go back to that first problem and try to find the derivative thereof. I know that the derivative of this product should be this first one times the derivative of the second plus the second times the derivative of the first. Right? So we need to figure out the derivatives of the two small pieces. So this is the first part times the derivative of the second plus the second times the derivative of the first. And we can say that this derivative is 27 x to the 8th, right? You said 9 times 3 give you the 27, and then decrease that power by 1. And likewise, this is 4x. So now let's put the pieces in that we need. Here are our derivatives that we throw in there, and now we can add these, or multiply these together, and add if we can, right? So in this case, this gets the 27 and the 2 gives you the 54, sorry, and you get x to the 10th. Likewise there, and then since they're tenths, we can combine them, right? X to the 10th, so you get 66x to the 10th. This is too much work for this one, right? Because we can combine this and simplify it earlier. But I wanted to show you that it does work to use the product rule. Okay, so let's try another one. Here's the product rule. Here's two functions, and I want to differentiate them. Well, the two pieces are u and v, so that's the u, that's the v, right? We're going to need their derivatives individually. So the derivative of this is just 3x squared, right? The 3 multiplies in front and decrease the exponent by 1. And the derivative of this is just 2x. From there, we can follow the product rule that says we have the, I guess they're using the first times the derivative of the second, that's this piece, and plus the second part here times the derivative of the first. And if you simplify that, distribute in, and clean it up, it should turn into that. And so this is the derivative of this function once it's been cleaned up. Okay, we want to be able to do the same thing when we have two functions being divided, right? This is the quotient rule, and here's the derivation if you're interested. Nope.
I want to take q of x, and eventually I want to find a rule that talks about q prime of x, right? The derivative of q prime of q of x. So one way to start thinking about this is maybe if we multiply both sides by v of x, it cancels out of here, and here's v of x over here. And so this and this piece are fundamentally the same. Vx, qx should be equal to ux, right? Well, now we have the product rule that we could use, right? And the product rule says take the derivative of the first times the second plus the second times the derivative of the first. And so there's this laid out for you. That's the derivative of u to the x. We don't want the derivative of u to the x. We want to isolate q prime of x. So we're looking to isolate this piece. So let's get all the rest of it off of there. Let's subtract this from both sides first. That's this piece, right? And so this is sitting by itself over here. And then they do a little bit of fancy algebra work over on this side. By calling q of x, we're just replacing it with q of x's original name in the first place. So instead of calling this piece q to the x, right? They just switched this whole thing. They just flipped the thing over. Instead of calling it q to the x, they called this ux over vx. That's that piece. Cool. And then I think they give some common denominators and do some denominator work. Right, so you get all this mess over v to the x. We still have to get rid of this v to the x, so you divide, so this becomes squared in the denominator. All right.
So that's the quotient rule. It's really similar to the product rule, except that you have a subtraction and the order matters in the top, and then you have this division by v to the x squared. Again, it's in your notes, wherever they went. But let's try to use it first. X is ux over vx, then the derivative of that is the derivative of the top times the bottom minus the top times the derivative of the bottom. The order matters. And you divide by bottom squared. That's kind of how I think about it. Or here's another way to write it, right, like this. It's a little more simplified. Derivative of the top times the bottom minus the top times the derivative of the bottom over bottom squared. Cool. Let's try one. So we want to use the quotient rule to solve this. I want to find, we want y prime, right? We want the derivative. So let's find what u is, right? U's the top, v's the bottom. Find the derivatives of both of those. So u prime should just be 3, and v prime should just be 2x. From what we learned yesterday, now apply the quotient rule. Okay, so we'd say, all right, well, here's the u prime, there's the 3, times v itself, so that's this. And then we take the u and multiply by the derivative of the v, and then divide by v squared. Cool. That's awful, but you can clean it up. And if you clean it up nicely, it turns into that. And that's our solution. But it's the derivative of this big ugly mess. Okay, so there you go. You've survived the product and quotient rule. I dubbed the mathematicians. Good luck, and we'll try a few problems next time we see you.